Hello students, welcome to this session. In this session, we will discuss about the block diagram reduction technique that we can use to solve the complex block diagrams for our control system. So first of all, we'll see what is actually the block diagram. So block diagram actually is a shorthand pictorial representation of the cause-effect relationship of a system. And normally the interior of the rectangle representing the block usually containing the description or the name of the element or the gain of the element or the symbol of the element and maybe the mathematical operation that that particular element is going to perform. So likewise, we can have multiple sub blocks or multiple blocks in a complete block diagram interconnected depending upon how they are interacting with each other in real world. So the block diagram becomes a small circle also known as a summing point with the appropriate plus or minus sign associated with the arrow entering into the circle. The output is the algebraic sum of the inputs. Any number of input may enter in summing point. Some blocks put a cross inside the circle also, but majorly we have to focus on the direction of the signal and the sign of the signal. Based on that, we can calculate the resultant output from that summing block. So one term is summing block. The control ratio of the closed loop transfer function is known as the C by R, that is equal to forward path gain GS divided by 1 plus minus GS into HS. So in this, that plus minus sign based on the whether there is a forward positive feedback or negative feedback. If there is a negative feedback, then the sign will be plus. If there is a positive feedback, then sign will be minus. The denominator of this particular transfer function, that is closed loop transfer function, is known as the characteristic equation. So sometimes we have to also find out the characteristic equation of the system. So from the complex block diagram, if we are able to simplify that block diagram and if we are able to find out the final block diagram or block with numerator and denominator. So the denominator of that particular transfer function represents the characteristic equation of that complete system. So there are certain rules that we should follow to solve the block diagram. So basically, there are 8 major rules that we should follow. If we understand all those rules, then it will be very easy for us to estimate the transfer function of any given complex block diagram. So the first rule is, let's say if two blocks are in cascade, that means the output of one block is going into the input to the second block. In that case, the resultant block we can have with the multiplication of the gain of these two blocks. That means if G1 and G2 are in cascade or in series, then the resultant block will have a transfer function of G1 into G2. If we have a block diagram where two blocks are connected in parallel, so how do we know that blocks are connected into parallel? The signal direction in both the blocks will be in same direction. Now, if we observe in this particular block, the second block, the signal that is flowing into G1 and the signal that is flowing into G2, both are in same direction, left to right. So that's why we say that these blocks are in parallel. The only thing that we have to remember apart from the direction that which particular signal is carrying what sign. So if both the signals are carrying positive sign, then the resultant will be G1 plus G2. If both the signals are taking negative sign, then it will be minus G1 minus G2. But here in this particular block, we are having G1 plus sign and G2 plus or minus sign. So based on that, the output transfer function will be G1 plus minus G2. Now, if we compare this new block diagram with the previous one, in the previous one, the direction of the signal in both the paths were same. But in this, if we see, the direction is one path is opposite to the direction in other path. So that particular type of loop is known as the feedback loop. In this particular loop, how we can identify? One direction will be in forward direction, then the other direction will be in reverse direction, where this G is known as the forward path gain and H is known as the feedback path gain. And the final reduced transfer function for this type of loop can be estimated as G upon 1 minus plus GH. So minus, if we have positive feedback, then we will have a minus sign in denominator. If we have negative feedback, then we will have a positive sign in denominator. Now, in most of the cases, if we have H1 is equal to 1, that means there is no feedback gain, then we can consider H is equal to 1, and we simply put H is equal to 1 and we get the final gain as G upon 1 minus plus G based on positive or negative feedback. So in fourth rule, if we observe, we want to move this particular block ahead the summing point, or in other way, we can say that we want to move this summing block to beyond this particular gain. So simply the basic rule to calculate the new gain is, if you see at this particular point, what is the output that we are getting? So let's say if this signal is X and this signal is Y. So here we are getting Y minus X into G. So here we are getting Y minus X into G. So if we are moving this G to this particular side, now if we don't use any gain here, what we will get here? We will get simply G into Y, and if this is X, G into Y into minus X. That G is missing. So simply what we have to do, we have to put a gain of G here. Now if you check here, you will get the same output. So this is how, even if we don't remember the rule, we can see that the final output of your block diagram should remain same. The other rule is, let's say if we want to move this particular block ahead to the summing point, then we have to use a gain of 1 upon G. Now, this rule number 6, similarly, if we see that we want to move this pick off point or takeoff point ahead to this particular block. So what are the changes that we have to do? Simply, let's say if this is X input, what will be the output? The output is X into G. And what will be the output here? It is X only. Now we have moving this particular block G ahead to this takeoff point. That means if X is here, at this particular point, you will get G into X. And so as if we don't use any gain here, we will get G into X. So, but what we actually want, we want X. So what we have to do, we have to multiply it by 1 upon G. Now, if you check in both the blocks, we are getting the same output. Now, in this particular case, simply we can check the final output here. Let's say if this is X, so here we are getting X into G. So to get the same output here, what we have to do, we have to multiply G here. That's it. Now, the eighth point, if we have two summing points and we don't have any block or any gain in between these two summing points, that means we can exchange or interchange the location of these two summing points. So likewise, we can apply those rules and we can solve the block diagram reduction problem in any of the given questions. So thank you for your kind attention.